The surprise is that the hardest part of manufacturing in space is not making things. It is proving you made them correctly every single time without sending them back to Earth. As of 2026, Earth is still the only full-stack manufacturing base. Mining, refining, machine tools, chemicals, electronics, metrology, labor systems, and standards are overwhelmingly terrestrial. Space hardware, by contrast, is still mostly launch and deploy. Satellites, stations, probes, and landers are built on Earth, integrated on Earth, and launched as finished or near-finished artifacts. Repairs are rare because every repair implies logistics, risk, and specialized tools. So when people say in-space industry, they are talking about a capability shift. You stop launching finished artifacts and you start producing propellants, materials, components, and structures off Earth. That shift is constrained less by a single printer or robot and more by qualification, logistics closure, contamination control, and the absence of a complete off-world industrial stack. Here is the first high-impact finding. In-space manufacturing is primarily a trust problem. If a part is safety critical, a third party has to believe it will behave as promised. On Earth, you can do destructive testing, audits, and rework. In orbit or on the Moon, return to Earth testing is expensive, slow, and often impossible. That pushes the burden onto inspection, traceability, and process history. The key question becomes, what is the minimum information record that makes an off-world part trustworthy? That idea sounds bureaucratic, but it is the gateway to scale. A minimum information build record is not just a serial number. It is a structured account of how the part was made, which machine made it, what the sensors saw, how it was calibrated, what the environment was, and which anomalies occurred. Without that, every mission becomes a bespoke argument. With it, certification can compound, because Mission 10 can rely on the evidence from missions 1 through 9. Second finding. Final inspection alone is rarely enough. In harsh environments, defects can be subtle, and failure can be catastrophic. A tiny void in printed metal, a contamination film on a seal, or drift in a sintering cycle can pass a surface check. That is why the focus shifts to automated inspection and anomaly detection, even when you do not have many examples of failure. Early space factories will not have huge datasets of known bad parts. You need methods that can flag outliers and detect drift when the definition of bad is still being learned. That also changes payload thinking. Sensor suites, calibration checks, and inspection compute are not nice-to-have software. They are core mass. If you fly a manufacturing demo without rich telemetry, you get a one-off stunt. If you fly it with disciplined data capture, you get an asset that makes the next demo cheaper to certify. Third finding. Computational materials modeling is a lever, but only after validation. Simulation tools can help predict microstructure, strength, and failure modes, and reduce how much destructive testing you need. But in-space conditions are not a rounding error. Microgravity, vacuum, radiation, dust, and thermal cycling can break assumptions. Until models are validated against those environments, simulation is guidance, not proof. The strategic move is building pipelines that connect simulation, process telemetry, sample testing, and qualification records. Fourth finding. Contamination and industrial hygiene are mission constraints, not paperwork. Closed environments amplify every mistake. Particulates, volatile byproducts, heavy metals, and even sensor fouling can halt operations fast, especially near habitats. Recycling heavy systems are attractive because launch mass is precious, but recycling also concentrates hazards. So contamination governance has to come before closed-loop scaling. You need exposure budgets, material inventories, hazardous byproduct tracking, and clear habitat interfaces, or you will discover the limit the hard way. Fifth finding. The real scaling barrier is institutional, not just technical. Long transitions punish organizations that reset learning every program cycle. Missions slip, teams rotate, suppliers change, and standards evolve. What matters is dynamic capability, the ability to reconfigure resources and routines without losing accumulated learning. That means building institutions that keep knowledge alive, participate in standards, and treat calibration, metadata, and auditability as enduring infrastructure. When you look at the timeline, the near horizon from 2026 to 2050 is likely dominated by demonstrations, servicing, assembly support, and early resource processing trials. A cislunar industrial layer between 2050 and 2100 is plausible, but not assured. The base case is maintenance depots, propellant logistics, modular construction, and limited local materials processing. Farther out, large off-Earth construction networks are physically permitted, but confidence depends on energy, robotics, and governance maturing together. A final caution matters for strategy. There are failure modes that scale with ambition.